Our next speaker is Marco Finocchiaro, who's going to talk about simplicity constraints in spinform models.
Thank you for the introduction. First of all, I would like to thank the organizer to invite me to speak this afternoon. Today I will talk about the imposition of simplicity constraints in spinform models, prescriptions, and implication. So here is an outline of my talk. Given that there are people from many different approaches in the audience, I will start with a very pedagogical and brief introduction to spinform models. I will then introduce two examples of spinform models for Euclidean quantum gravity as constrained BF theory, the well-known APRL model, and a new class of models, the proposed by Aristide Baratin and Daniele Riti. And in part 3, I will try to compare this new kind of model that we have with the APRL model by studying the behavior of its fusion coefficients in the large J regime. So, of course, I will be much clearer in the next slide. So let's start with an introduction to spinforms. We might define spinforms as models for quantum spacetimes that are built, that are intended to provide a covariant description for the dynamics of network states, spin network states, but also generalizations. And the basic idea behind the construction of spinform model is to use the reformulation of gravity in terms of constrained BF theory. So that we start from classical topological BF theory in 4 dimensions. The action is given in this exponent here. We discretize this theory on a simplicial complex, and considering so a simplicial complex delta and its dual to complex delta star. In particular, we replace the manifold M with delta, and we replace the continuous variables B and omega. The B is a bivector, and omega is the spin connection, if we are talking about Euclidean models, with a set of discrete variables obtained by smearing the continuous variables on the subsimplices of delta and delta star. In particular, the bivector is a 2-form here, and it's smeared along the faces, so the D minus 2 simplices of our 2 complex, while omega is a connection, and it gets smeared on the lines along these red edges of our 2 complex. So then we basically quantize the theory by writing down a partition function for it, which is nothing else than the requirement of having trivial holonomies around the faces of our 2 complex. If you perform the integration on this bivector, you get basically a bunch of delta functions enforcing the triviality of this holonomy along the faces. Now the non-trivial part comes into play, and it is related directly with the imposition of the geometricity constraints, which will turn simplicial topological BF theory into quantum simplicial gravity. I should say in advance that there is a huge literature concerning the imposition of the simplicity constraints in the context of spinform models. For what concerns my talks, I will deal with the linear simplicity constraints, which are nothing else than a particular relation between the self-dual and anti-self-dual components of this bivector, of this element of spin 4. Here, case is an element of S3, and it plays the role of a normal, which is actually associated to the tetrahedra. So the key point to keep in mind here is that this simplicity, these linear simplicity constraints, are second-class constraints, and so they cannot be imposed directly as strong operatorial equation, and that this is one of the many issues that actually we have to face in the construction of spinform models. One issue is indeed the definition of prescription for imposing the linear simplicity constraints directly at the quantum level. There is the so-called master constraints technique, the imposition via star multiplication with non-commutative delta function, and there are also other techniques that have been proposed in the literature. This is not the only issue, as I said, in which we have to face when trying to construct spinform models. We have also to deal with the choice of the quantization map, that is, with the choice of the operator order ambiguities. Here the quantization map, just to recall this briefly, is a map from an algebra A to an abstract operatorial algebra U, which this property which have been summarized on line number 2. Here by A of G, I mean a subalgebra of the algebra of the smooth function, which are actually constant on this second argument here. And the third point is the additional choices that we might want to consider in the construction. That is basically the prescription for gluing simplicial cell, the prescription for gluing this tetrahedra when we are in 4 dimension, actually to gluing for simplices around tetrahedra and triangles. We might want to start with building blocks that already have encoded all the geometricity constraints, or we can force the geometricity constraints directly when we glue more simplices to build our simplicial complex. Both cases will deal us to different models. So for what concerns my talk, I will mainly deal with point 1 and basically the 2 models that I mentioned at the very beginning, the EPR model and DBO model, are 2 examples of model which implements the first, the master constraints technique, and basically the technique of the non-commutative, the implementation of the constraints via non-commutative delta function. The important remarks, so before giving the definition and all that we need about these models, these 2 models that I will consider later on, 2 important remarks. The first one is that always, in the case of simplicial spinform model for constrained BF theory, whatever is the prescription that we use to construct the model, whatever is the choice of the ambiguities in the operatorial ordering, we always end up with amplitudes associated to closed complexes which take the following form. They are basically a product on all simplices, on all vertices of our 2 complex of vertex amplitude, AV, where the vertex amplitude is defined in this way. It's a product of 15J symbols associated to the left and right part, to the minus and plus part of Spinform, which decompose in 2 copies of SU2, times this object here. There is one of these object for each edge, so one of these object for each tetrahedron, which are called the fusion coefficients. So these fusion coefficients actually are a map from the space of 4-valent SU2 intertwiner to the space of 4-valent spin4 intertwiners. Intertwiners are indeed element of the trivial subspace of the tensor product of representation. So therefore, because this is the general form in the case of amplitude for closed simplicial complexes, to compare different models, which comes from having chosen different prescription to implement the constraints, it is already enough to perform a preliminary comparison. It's already enough to focus on the behavior of these fusion coefficients, because it's precisely in this object that all the information concerning the way we have chosen to impose those constraints is actually coded. So here is the APRL model. I'm considering here the original APRL model proposed in this paper by Engel, Pereira, Rovelli, and Etera-Levin, and a slightly modification of this model, which has been proposed later on by Sergei Alexandrov. The idea behind the construction of these 2 models is basically to impose, as I said, the simplicity constraints via the master constraint criterion. That is, we quantize the bivector we identify them, so x minus and x plus, with the minus and plus generators of the SU2 left and right, on which I can decompose spin 4. And I look for the minimal eigenvalues of these master constraints here, which is defined in this way, where this is simplicial operator is just nothing else than the quantum version of these simplicity constraints here. If we do this way, we actually solve this condition. Well, solve is in quotation mark, because actually we're not annihilating him, we are just minimizing him. We find this two set of solution for these two different regimes of beta. Beta is basically what is called in the lecture the Mirzi parameter. And it is important for many reasons. One of that is the connection with LQG. The solution proposed by Sergei Alexandrov are slightly different, as I said. They coincide when beta is between minus 1 and 0. They are a bit different in the other case. In both cases, the expression of the fusion coefficient is given by equation 5 and 7. You note here that the only difference is what is inside these square brackets, because basically the intertwiner's structure is the same, and it comes, well, from having also imposed the closure constraint, the discrete analog of the Gauss law. So far for the APRL models and the Alexandrov modification of that model. Now we can introduce the other candidate, the BO model, that later on we would like to compare to the two models that I have introduced just in the slide before this one. To do this, I just need to recall a few very basic definitions about the non-commutative Fourier transforms. And basically, it is a map from the square integral function on L2 on the group to the square integral function on L2 on its Lie algebra. The BO model is basically constructed by implementing the constraints by appropriate insertion of non-commutative delta functions enforcing the condition. The amplitude for these models is given by equation 10. What is matter now is that if we go back to the very first slide and we keep in mind this expression, the only difference is just given by these round brackets here, which contains the constraints. So here is the expression for the fusion coefficients of the Baratin-Oriti model. The main remark that we have to care about is that we have a much more general condition relating the J minus, the left and the right spins, if compared to the case of the APRL model. Now, in order to compare, so since the intertwining structure is basically the same, in order to compare these fusion coefficients to the expression that we have, that I showed you before for the APRL models, it's already enough to look at the behavior of this simplicity function S, which have been defined in equation number 14. To do this, we can tackle the problem. Well, we can look, for example, at the large J regime. We can look what's the behavior of this function in the large J, and now I have to summarize basically the result. The idea is to rewrite this function in terms of non-commutative, in terms of the non-commutative Fourier transforms of the Wigner matrices. And the important part here is that this function here, this Bessel function here, for large J's, peaks around this configuration, which basically means that in the large spin regimes, the integrand of our simplicity functions turns out to be localized around x plus minus modulus equal to dj plus dj minus, which this is just 2j plus 1, basically. Now, if we look at this function here and we replace modulus of x with dj minus and modulus of x plus with dj plus, as we did here. Since this function, as is shown in this plot here, this function here is basically peaked around the argument being 0, we find that the constraints implemented by the weighting function of the Baratin-Oriti model are actually in the large J limit given by the APL solutions. So, okay, I will skip the other technique, which is well, a direct study basing on the not on the flux representation, but on a rewriting different way of rewriting this integral here using a particular formulas for the Wigner D matrices. This is actually very nice because allows us for exact numerical evaluation of the fusion coefficients. And I just conclude summarizing the main results of my talk. So according to our preliminary analysis, the BO model simplicity function in the large J limit seems to peak around the solution of the PRL model. The analysis is still preliminary, but this is already a non-trivial result. The Alexandrov solution lies also quite close to the peak of this plot, which means that basically they can also be considered as good solution, good weighted solution by the BO weighting function. The derivation of this result is, by the way, not fully satisfactory, so for several reasons. We have just looked at the behavior of the integrand, not the full integral. A more precise and extended analysis of this class of GFTs and Spinform models based on an explicit numerical evaluation of their amplitudes and fusion coefficients is actually in progress. And yeah, we might want to tackle later on many issues that I leave just here. One of these is, for example, the asymptotic analysis and the counting of the degenerate and the non-generate configuration that we get as a solution of the saddle point equation. And of course, the issue of the renormalizability of this class of simplicial GFT Spinform models. This is what I want to say for today. Thank you for your attention.
Is there any question? Okay, if no, we can thank our speaker again and go on with the next one.